Chapter 2, Exercise 26. Hints. First, prove that in a metric space with a countable base, every open covering contains an at most countable subcovering, the Lindoff property. Then use the given hint. Solution. By example 23 and example 24, the space X has an at most countable base, here, where B is an at most countable set. First, we will prove that every open cover in the space X contains an at most countable subcover. Let this be an open cover of X. For every alpha, there exists a subset B of alpha subset of B such that this. Let C equal this. The set C is a subset of B, hence C is at most countable. For every beta in C, we fix an index alpha of beta such that this. In particular, this, since this. We will show that this is an at most countable subcover of this. The inclusion here is obvious. Let X element of this. There exists alpha 0 such that X element of G alpha 0. Since this, there exists beta element of B alpha 0 subset of C such that this. So, X element of this and this. Thus, every open cover in the space X contains an at most countable subcover. It remains to show that every countable open cover of X contains a finite subcover. Assume the contrary. That is, assume that there exists a countable open cover G1, G2, and so on of X. X equals this. That does not contain a finite subcover. For every positive integer n, this. Hence, there exists a point xn element of this. Let E equal this. The set E is infinite. Indeed, for any positive integer n, there exist sets here such that this. Let n be the maximal index of J1, J2, and so on to Jn. Then, xn not an element of this, and xn is distinct from x1, x2, and so on to xn. Since the set E is infinite, it has a limit point y element of E prime. For some index n, y element of Gn. The set Gn is open, so there exists a delta greater than 0 such that this. The neighborhood n delta of y contains infinitely many points of E by theorem 220. Consequently, Gn contains infinitely many points of E. On the other hand, for all n greater than or equal to n, xn not an element of Gn, which means that Gn can only contain points x1 and so on to xn minus 1. This contradiction proves that the covering here contains a finite subcovering and that X is compact. Comments. Theorem 237 states that every infinite subset of a compact space has a limit point. From example 26, we see that this property is equivalent to compactness. Thanks for watching.